Hi, I'm Liang Tao. Shihao is the team leader, and Mingxian and Luoyu is our team member. And we are going to present our final project file system. This is our role and responsibility, and the software architecture is designed by Shihao and me. For the implementation, I'm responsible for implementing the low-level memory management, and Shihao is responsible for inode operation and command processing. Mingxian is responsible for backup and restoration, and also dump file encryption and decryption. And Mingxian is responsible for Vim file editing. And below is our percentage of our role. And before we introduce our code, we would like to show the system demo first. And first, we create a new space with. Okay, so first we create a new space with 20 megabytes partition size. And we will initialize the root first and check on our file system status. So as you can see, we have one inode user in use. That is our root, and we have 0 block file. Okay. And next we want to show the ls command to check our list, and you can see there is no other file or folders under the list because we haven't added any yet. And we will try to use make directory to create a folder named test. Okay, we use ls to check, and you can see there is test under the root. And we can also use multiple paths to create a directory. And so now we create a test2 folder under the test directory. And we use cd to move into test folder and use ls to check. As you can see, there is a test2 folder under the current path. Then we can also use absolute path to create a directory. And now we create a folder under root named test3. Go back to root and check for test3. Okay, you can see there is test and test3 under root directory. And in our system, we can use relative path, absolute path, or multiple paths as input. And now we try to use absolute paths to remove test2 folder. And we cd into test file to check. Okay, there is nothing under the test file. And for the next part, we want to present the file operation in our system. So first we use put to put a photo into our system, and the size is 7.76 MB. So we use put command to put the large photo into our file system. We can use ls to check. There is a photo under the test directory, and use status to check. And the files blocks used is 7,000, almost 8,000. And then we try to get the photos in our file system and restore it into our computer file system. Okay, and then we check on the dump folder. Okay. And next we want to show the create file command, and we create a text file and check there is a there is a text file under the test directory, and we can try to use edit to write something into the text file. And now we open the Vim editor. We use Vim as the text editor, so you need to have Vim installed in your PC. And we type in hello world and save it. And then we use cat command to print out the text we just edit. And the terminal will show the word. So the next command is to get the text file into our PC file system. Then we check on the dump file. Okay. Hello world. Then the next command is remove. So now we try to remove the photo we just added into the file system. And use ls to check. And use status to check on our system info. As you can see, the file blocks is changed to 1 because we have one text file in our system and the photo is removed. And then we can try to save and load our system. First we use exit and enter the password to encrypt our dump file. Okay. And check in our PC there is a my fs dump. Then we start our program again and use and choose load from file. And then first we try to enter a wrong password, and the terminal will show password incorrect and exit the program. And then we run again, and this time we try to use the correct password. Okay, and then the system will load again, and we can type something to check on our system. Okay, as you can see there is same as before, and you can use ls to check the file, the folder, and cd to test to check on the text file we just added. Okay, show hello world. So yeah, there is our demo. And then we will introduce our system architecture, and our system is combined with 4 parts. The first is user interface and command processing layer, and then inode management, and the last one is memory management layer. And the user's interface layer contain a main file and responsible for programming entry point and user interface and command parsing. And the command processing layer has 3 files: command.c, dump.c, and edit.c. And the command is responsible for main command processing, file and node management, and file operation. And then the dump C is to save and load system state and encryption and decryption of the dump file. And then the last is edit. Edit is to do text editing, text file editing. And the node management layer contains a node.c file and is responsible for root initialization and directory management. And the last is memory management, and it is responsible for low-level space management, memory allocation, inode allocation and release, data block allocation and release, and low-level read-write operations. And then next is our memory structure. So the block size, each block size have 1k byte, and this is our memory structure. First is the super block, and then the inode and data bitmap. Then is the inode block. The inode block is 10% of the partition size, and the remaining block will be data block. And then is our inode and super block structure. So in our super block structure, contain the information of our system, like partition size, system block, and user block, etc. And then in our inode, we have the index, and is the boolean of is file is to check whether it's file or folder, and a boolean of is used is to check whether the inode is used or not, and the size of the inode. And we have two array of int. One is direct block and one is indirect block. Direct block is an array that contain data block index directly pointed to the data block, and indirect block is each element direct to a direct block, and each direct block contain 256 element, and each element can direct to one data block. So as the size of direct block is approximately to 64k byte, and indirect block max size is approximately 16 byte. So each inode can contain this many size of data. And the first part is space, and I'm responsible for implementing space. So the first function is init space. The function is to allocate memory for our new file system, and calculate and divide all the space into the system, including memory super block, bitmaps, inode table, and all the data blocks. And then set up memory pointer to each region, and last is initialize super block. And then the next function is allocate inode. This function is to search the first unused inode in the bitmap. So it will check the bitmap to find the unused inode, and then if it's found, it will mark the inode is to used in bitmap, and then initialize the inode, set the information of the inode, and change all the direct block and indirect block into -1, means there is no data block assigned to the array. And the next is allocate data block. This function is same as inode. Allocate inode is to find the free data block in bitmap, and then if it's found, change it to used in bitmap, and then initialize data block with all zeros. And next is get inode and get block position. Both function is input the index of inode or the index of block, and then it will return the pointer, the inode pointer or the block position pointer. It will return no if the input is invalid or the block is unused, the inode is unused. And the next function is allocate single block for inode. This function is to try to use first it will direct a block to a data block to the direct array. If the direct array is all full, it will try to use indirect block to allocate memory, a data block. So, and then the allocate empty int array block is to initialize the indirect block. It will find a new block for storing block pointers and initialize all the elements to -1. Means there is no block assigned to the pointer yet, and return the block number. If return -1 means the allocation is failed. Next function is allocate data block for direct block and indirect block. So the first function is to search an empty slot in direct block array. So if it finds a -1 elements, it will allocate a new data block for it using the function allocate data block we just introduced. And the next is allocate data block for indirect block. So it will initialize the indirect block if the slot is empty. So if it's -1, it will initialize the indirect block first using the allocate empty int array blocks. And then if the block is already assigned, it already exists, it will check for empty slot and use the allocate data block for direct block function to assign a new block. Okay. Next function is allocate block by size for inode. So basically it will allocate block depends on the size. So it will calculate the block needed first, and then allocate block one by one using the allocate single block for inode. It will allocate one block each the time, and it will handle allocation failures with rollback mechanism. And next is free data block and free inode. Free data block will input is the block number, and it will check if the block is in use or not. If it's in use, it will mark as free and then update the usage of counter. And next is free inode. Free inode is also do the same, but managing the inode bitmap and also release all the block associated with inode. So it will first release all the direct block and then release all the indirect block using the free data block function, and then mark the inodes as free in bitmap and update superblock usage. So the next is write block and write file data. The write block is to write data into specific block in file system. So, and it will ensure the write size doesn't exceed the block size, and use the memory copy function to copy the data into the block. And then is the write file data. So this function is the first will allocate the needed block for the file. So it will calculate it will get the size of the file and then use the size to allocate data block by size for inode using the function we just introduced. And then it will try to write into direct block first. If it is full, it will try to write into the indirect block. And the write direct block in indirect block function is to write data directly into the block using block index, and then update the pointer and remaining size. So it will continue until all the data is written or there is no more block. So if the direct block is full, it will continue to write into the indirect block using the same method. Okay. Next. And next is read blocks and read file data, and it is basically the same method as the write block, and the difference is only to read the data from our file system and then copy into the buffer and return back to other function. So I will skip this section, and the read direct block also the same as the write direct block. And next, so the last two function is load file system and destroy space, and the load file system will first take the raw data and reconstruction the file system, and then set up all the pointer to the different region in memory based on the parameters, the informations in the super block. And then destroy space is when you save your file into dump file, it will destroy the space, free the raw space and file system allocate in our memory. And there is my part. And next is 示好.
Okay, I'm Shihao. Next, I will explain how the main command demonstrated in the demo are implemented. First, let's look to our main function. It's very simple and only handle the initial function selection. There are two options. One is to read a file, which can read a saved and encrypted dump file, and the other is to create a new space where you can input the space size. If we choose to read a file, the program will promote the user to enter the password to decrypt the file. If the decryption is successful, it will enter the interaction function for command interaction. If the decryption fails, the program will stop. The detail of how to read and decrypt the file will be explained by other teammates later. If we choose to create space, the program will read a partition size entered by user and initialize the space according to the size. The method of initialization has already been discussed by the teammate earlier. After that, we can create a root, and once the root is created, it will also enter the interaction function. The method to create the root is to initialize an inode and allocate a block space for this inode. We create a directory entry object which stores two pieces of information. Similar to a key value concept, the key is the name of the inode, and it points to, and the value is the index of the inode. So we can create a directory entry with the key as the dot and the value as the root address, and store it in the block. The function responsible for writing the directory entry will handle this. It checks if the space in the block under the inode. If there is space, it writes the entry. If not, it allocates a new block and then write the entry. In the interaction function, the main process is within a while loop. Before the while loop, we initialization an inode pointing to the root to keep track of the current path. Then we enter the loop using a switch case to call different function based on the user input command. If the command is to save an X, the user will promote it to enter password, and the system will save the file and exit the loop. For other commands, after execution, the loop will continue. Let's start with the simplest command, ls. In the file system, an inode under a path can have many blocks, and these blocks are stored directory entries which store names and point to the next inode. So ls doesn't have much to do. It simply finds the block under the current path and lists the name stored in the directory entries of all the blocks. Before discussing other features, I need to explain a model that is used in almost all functions: the path splitting and processing. The same command might involve a single relative path, a multi-level relative path, or an absolute path. So we need to handle all three cases. First, in the interaction function, we are already split out the path parameter. Then in the specific function, we determined if the path starts with the /root, which indicates an absolute path. If it is an absolute path, we set temp path to the root. Otherwise, we start with the current path. We will then search downward to see if there is a path matching the path parameter under temp path. If not, we exit early. If there is, we continue searching until the search is complete. It's important to note that in different function, what we do when exiting early, completing the search can differ. For example, in the cd command, if we exit early, it means the path cannot be found, and we return the interaction function. If the search complete, we actually change to that path. On other hand, for the mkdir command, if we exit early, it means we need to create the corresponding path. If the search complete, it means the path already exists and no action is needed. Now, let's discuss the cd command, which is very simple and use the path processing we talked about earlier. If the search completes, we set current path to the temp path. If we exit early, it means the path cannot be found, and we return immediately. Next is mkdir command, which is also quite simple and use path processing. If the search completed, it means all paths are already exit, so no action is needed, and we return immediately. If we exit early, we proceed to create the corresponding path. First, we initialization a inode and allocate a block space for this inode. We create a directory entry object pointing to itself and another pointing to the parent path. Then, we create a directory entry for the parent path pointing to the new path. Finally, we store the three directory entry into the corresponding block. If multiple paths need to be created, we repeat the process multiple times. The next is the rmdir command, which also use path processing. If we exit early, it means the path does not exist, so no action is needed, and we return immediately. If the search complete, we check whether the target inode is a directory and whether it is empty. If both conditions are met, we remove the directory entry from the parent inode. Finally, we free the inode and its blocks. With path-related command explained, handling file with RM is very similar to rmdir and use path processing. If we exit early, it means the path does not exist, so no action is needed, and we return immediately. If the search completes, we check whether the target inode is a file. If it is, we remove the directory entry from the parent inode. Finally, we free the inode and its blocks. The create command is similar to mkdir and use path processing. After finding the target path, we create a new inode and allocate an empty block for it. Then we create a directory entry from the parent path pointing to itself and store it in the corresponding block. The put command brings a file from the external environment into the system. It does not use path processing, but directly check the file exists externally. If it does, it is similar to create. We create a new inode, allocate block sophisticate to store the entire file, and load the data into the block. Then we create directory entry from the parent path pointing to itself and store it in the corresponding block. The cat command is a relatively similar function, simple function. It prints out the content of a file, so we just needed to use path processing to find the inode corresponding to the file. Then we read the file content from the blocks under the inode and print it. The get command is similar to cat, but instead of printing the content, it uses fopen and fwrite to write the content into the actual environment. Okay, that is my part.
Okay, then we are going to introduce our dump and the encryption and decryption function. And the first part is the created dump function, and this function is for the entry point for the backup functionality in the file system, and it can generate an encrypt dump file to save the file system state for the future recovery. And the first part of future create dump is the file name. The default file name is the my fs.dump file, and it's stored in the file name variable with the size of 256. And next part is the password, and the function prompts the user to enter a password for encryption, and if the input fails, it will display an error message and exit. And next part is it will remove extra new line character, and you can see at the new line character in the password will be replaced with a null parameter to ensure the correct formatting. And next part is when it's going to save, it will call the save the file system to cause the save to dump file to encrypt and save the file system data into the specific file using the password. And finally, it will return the result if untrue answer says and otherwise false and in if it failed any steps. and going to the next part is the save to dump files function. And this part is the core function responsible for encrypting and saving file system data to a dump file. And the first part is opening the file, and it opens or creates the specific file in the binary write mode, and it will return false if the file cannot be opened. And the second part is the allocating memory for encryption, and this part allows allocated memory for the file system's encrypt data. And it also will exit with an error if the memory allocation fails. And the third part is it will copy and encrypt the data, and it will copy the raw file system data to the allocated memory and encrypts it in its using the XOR encrypt decrypt function. The next one will write the encrypt data to the dump file, and it will ensure the correct number of bytes is written. And the last step will release the allocated memory and close the file. So the key feature of this function is like the efficient encryption with the XOR operations. And the next part will show you how our XOR encrypt decrypt works. And this part is, and our XOR encrypt decrypt part is the utility function for the XOR based encryption and decryption, and it used throughout the module and to ensure the data confidently. Okay, so how it works is like the first part is to computing the password's length. It will determines the length of the password and enabling the cyclic application during the XOR operations. And it will apply the XOR operations, and it iterates through each byte of the data and applies the XOR with the corresponding password byte, and it will cycle through the password if it's shorter than the data. Okay, so this is make sure the encryption and decryption use the same function and the password, and it's very efficient for the lightweight applications like our this subject. And the next part is about the reading and restore dumps with our read dumps function, and this and read dump is responsible for the recovery from the file system state from the encrypt dump file, and it will decrypt the data using the user provide password and rebuilds the file system structures. Okay, so first part, it will ask for the user to input the password, and if the input fails, the function exits with an error. And next part, it will coding the load memory part, and this part will load and decrypt the dump file using dump file's content using the password, and otherwise it will return null if the file cannot be loaded. And next part will allocating the memory for the file system. This will make sure it allocates the memory for the file system structure to store the decrypt data, and also if the memory allocation fails, the function release any loaded data. Okay, and and then it will copy the decrypt data into the allocated file system structure, and finally it will return the reconstructed file system structure or null on the failure. So this part's feature is like secure the restoration of the file system data. Okay, this part of it is the load memory part, and this function reads the encrypt data from the dump file and decrypts it, and it will ensure that the data is ready for the reconstruction in the file system. Okay, so the first step will open the my file system.dump in the binary read mode, and then the next part will determine the file size. It will calculate the file size and resets the file pointer to the beginning. The next part will allocate in the memory. It will dynamically allocate the memory for the file's contents. It will handle the allocation failure by closing the files and exit. And next part will read file's content. It will read the entire files into the memory and checks for the completeness. And next part will decrypt the data. It calls the our encrypt decrypt function to decrypt the loaded data using the provided password. And final part will returns the decrypt data. It returns the pointer to the decrypt data for the further use. Okay, so the function of this is like the robust file handling with error checks, and make sure it's dynamic memory allocation or for files of the varying size, and also it secure the decryption integrate with the password protect data. Okay, so this is our dump and the encryption decryption part. Thank you.
So next, we will introduce the command process for 18, starting with a brief explanation of the architecture diagram. Enter command interaction. This is the stage where the system waits for the user to enter specific commands, and command input editor, and locate target file inode. The program resolves the path step by step to locate the target file inode and check if the file exists, and load file data into buffer. If the file exists, its content is read from the file system into a memory buffer, preparing for editing, and invoke external editor. An external editor is called to edit the file and modify its content, and write editor data back to data break. After editing, the modified data is read back from the buffer to the file system to update the file content. And finally, return to command input. Once all operations are complete, the system returns to the command input interface and waits for the next command. And path preparation and memory allocation. And first, memory is allocated using malloc to store a new inode structure. The path in inode is copied to temp inode using memcpy to create an independent copy. And arg is the comparative input path. Its length is calculated and starting a temp arg with the length of length. is declared to store a copy of the path. The input path arg is copied into temp arg's use struct p. And to press the path structure step by step, struct is used to spread temp arg by slashes and extracting each directory or file name in the path. And structure is used to find the position of the last flash in arg. And if last slash is not known, the file name is copied starting from the character after the last flash into file name. And if last flash is none, the entire arg is copied into file name. And next to the first character of the path is checked to see if it is flash. Determine whether the path is an absolute path. And the first part of the path is checked to ensure it is root. Let's confirm that an absolute path starts from the root directory. And if the path does not start with root, an error message. And stock is used to extract the next level of the path. The token is checked to see if it is none, confirming whether the path contains file name. If token is none, it's indicated that path pressing has ended, but a file name is missing. And this is directory traversal and path searching. And first, start by initializing variables to traverse the directory structure. And a while loop is used to process each part of the path step by step, ensuring that each extractor talk can be resolved as a directory or file name. And special directory name are excluded first. And the variable next path is used to indicate whether the next level of the directory or file in the path has been found. If a matched directory or file is found, the loop exits immediately. And next, all directed data blocks of the current directory are traversed. If a data block is merge 1, it means there are no more mirror blocks to check at the search end. And if the target is found next path is set to train and the loop exit. And this is directory entry traversal and target matching. And obtain the starting address of the current data block in memory. Initialize the offset as 0, and which will be used to traverse the directory entry within the data block. And iterated through all directory entry in the data block until either the block size is exceeded or the target is found. And this self or further is used to determine if the current directory entry is a special entry. And This is compare the file name of the current directory entry with the target file name to check for match. And let's compare the name of the current directory entry with the current pair of the path. And check each directory entry in the data block one by one until the traversal is complete or the target is found. And target path plus and data loading, and if the target cannot be found in the current path, exit the while loop and use stock to retrieve the next part of the path. And retrieve the metadata of the target file using file index and determine the file size to ensure the memory allocation matches the file size. And next, allocation sufficient memory to prepare for reading the file content, ensuring that memory allocation errors are avoided. And this is temporary file creation and data strategy in add buffer with min. And first, temp file name defines a base name for the temporary file. Next, temp create and open a unique temporary file, providing a temporary storage space for writing and editing the buffer data. And smprint is used to construct two backup names for the temporary file, facilitating tracking and managing different versions of the temporary file, and check whether the temporary file was created successfully, and ensure the file is opened successfully to avoid the issue where data cannot be written. And finally, ensure the buffer data is correctly written to the temporary file and immediately flashed to disk. And this is Vim editing and resource management, and using Vim to editor to contain content of the temporary file, directory modified into data within the file, and retrieve the file size after editing in Vim to check if the buffer size needs to be adjusted. And next, to check whether the file size has changed to ensure that the buffer size matches the file size. And relocate the buffer dynamically to adjust its size according to the new file content, ensuring stable memory allocation. And finally, ensure that the buffer's content and size are consistent with the modified file content. And read the modified file data from Vim back into the buffer for subsequent use, and close the temporary file to ensure the file stream resource and properly release, and delete the temporary file to clean up all temporary files generated during the editing process, avoiding wasted disk space or leftover just file. And finally, let's new inode creating and version replacement. And create a new inode to store the modified file content, ensuring that the old inode is not directly overwritten. and record the metadata of the new inode correctly, including the file size, and to facilitate subsequent read and write operations, and store the modified file data in the file system and associate it with the new inode, and update the directory entry to point to the newly created inode, achieving version replacement of the file content, and clean up resource occupied by the old inode, and release memory resource.